Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Identify the substrate. 1,2-dimethylpropylptoluene sulfonate is the tosylate of 1,2-dimethylpropan-1-ol, i.e., 2-methylbutane-1-vial tosylate. The structure is CH3CH, CH3, CH, CH3, OTS. More precisely, the carbon skeleton is CH3 to CH, CH3, OTS. This is 1,2-dimethylpropyl tosylate, meaning C1 bears the OTS and a methyl group, C2 bears a methyl group and is also a CH, and C3 is a CH3. Actually, let us be precise. 1,2-dimethylpropyl refers to the 1,2-dimethylpropyl group is equal to CH3, C2H5, CH type. The parent is propyl, 3 carbons, with methyl substituents at C1 and C2, CH3, C, CH3, OTS, CH to CH3. No 1,2-dimethylpropyl is equal to C1 has OTS and methyl, C2 has methyl, C3 is CH3, structure is CH3C, OTS, H, CH, CH3, CH3, i.e., 2-methylbutane-1-vial tosylate with OTS on C1. Weight 1,2-dimethylpropyl as a group means the propyl chain has methyls at positions 1 and 2, C1, CH3, OTS, H, C2, CH3, H, C3H3. This is 1,2-dimethylpropyl is equal to same as 1,2-dimethyl-1-propyl, meaning C1 is CH3, OTS, H, and C2 is CH3, H, giving overall CH3CH, OTS, CH, CH3, CH3, i.e., 3-methylbutane, 2-vial tosylate, a secondary tosylate with a beta-methyl branch. Moving on to the next step. Ionization. Under solvolysis, SN1E1 conditions, in acetic acid, the OTS leaves to form a secondary carbocation at C2 of 2-methylbutane skeleton, CH3, CH, plus CH, CH3, CH3. Actually, with the structure CH3, CH, OTS, CH, CH3, CH3, ionization gives carbocation at C2, CH3, CH, plus CH, CH3, CH3. This is a secondary carbocation adjacent to a tertiary carbon. C3 bears 2 methyls and 1 H. Let us recount CH3, C plus, H, CH, CH3, CH3, C3 is equal to CH, CH3, meaning C3 has 1 methyl, 1 H, connected to C2 and C4, CH3. So C3 is secondary. The initial carbocation at C2 is secondary. Moving on to the next step. 1,2-hydride or methyl shift. The adjacent C3 is CH, CH3. So a 1,2-hydride shift from C3 to C2 gives a tertiary carbocation at C3, CH3, CH2, C plus, CH3, CH3, 2-methylbutane, 3-vial cation is equal to tertiary. Alternatively, a 1,2-methyl shift could occur. And for the final step, A. Substitution with ACOH at C to CH3CH, OAC, CH, CH3, CH3, 1 substitution product, retention inversion counted as 1 product assuming no stereochemistry distinction here, or 2 if stereoisomers counted. B. E1 elimination, remove H from C1CH2 is equal to CHCH, CH3, CH3, but 1 Na derivative, 3-methyl but 1 Na, remove H from C3CH, 3CH is equal to C, CH3, CH3, 2-methyl but 2 Na. Products from rearranged tertiary carbocation, C3 plus, is equal to CH3 to C plus, CH to CH3, C, substitution, CH3 to C, OAC, CH to CH3, 1 substitution product. D. E1 elimination, remove H from C to CH3, CH is equal to C, CH3. Wait, cation is at C3 into methylbutane numbering after shift the tertiary cation, CH3, to C plus CH3 elimination gives CH3 to C is equal to CH3, 2-methyl but 2-Na, same as above, or CH3, C is equal to CH2, CH to CH3, 2-methyl but 1-Na. Substitution products, 1. CH3CH, OAC, CH, CH3, CH3 from secondary cation, 2 CH3 to C, OAC, CH to CH3 from tertiary cation. Alkene products, 3. 3-methyl but 1-Na, CH2 is equal to CHCH, CH3, CH3, 4, 2-methyl but 2-Na, CH3, to C is equal to CHCH3. From either cation, 5, 2-methyl but 1-Na, CH2 is equal to C, CH3, CH to CH3, from tertiary cation. Total is equal to 5 distinct products, 2 substitution plus 3 alkene. Options A, 2, B, 3, C, 4 undercount because they miss either the rearrangement pathway products or one of the elimination products. The full accounting of both cations and all possible elimination substitution pathways gives 5 products. Therefore, the correct answer is D. Therefore, the correct answer is option D.